Hi everyone. Today I want to share something very important when it comes to ship stability. In today's video, I am going to explain with an example how can density of water affect the trim of the vessel or even the waste distribution for the vessel, which can affect a list further on. I'll tell you the reason why I'm making this video. Now, when I was a master, I remember one of my chief officer, being a chief officer, he asked me that why are we so fussed about the density of water when it comes to stability calculations, because according to him the freshwater density may be 1 and the seawater density is 1.025, but when it came down to dock water density, it used to be very close to the seawater density, and he couldn't understand why there is so much fuss about finding the right density and making the calculations according to the right density if the value was so close to the seawater density, because sometimes we would get something like 1.020 or 1.019 or 1.021. He would just use the seawater density as the basis of calculation. Now, using an example today, I want to show you why it is very important and how it affects the weight distribution on the vessel. All right. So imagine this. Now, this is a ship's ballast tank. Right. This is a ship's ballast tank, and this ballast tank can hold up to, let's say, this is up to 1225 tons of salt water or seawater. All right, we call it seawater, or you can call it salt water, density of which is 1.025. Right. Now, if I pump out this water, let's say I pump out this water and I replace it with dock water. All right, I replace this tank with dock water. Let's say the density of which is 1.005 tons per metric cube. All right, this is 1.025. Right, and I replace it with dock water of density. So I have filled it up. Let's say it's filled up. The whole tank is filled up. It's completely full. I pump out the seawater and I replace it with dock water of 1.005 tons per metric cube. What difference does it make? So let's see this from an example point of view. Right, now I'll change the color of the pen so that you don't get too bored out of it. So when there was 1225 tons of salt water, what was the issue here? So let's say mass of salt water equals volume multiplied by density. You guys all know this, mass equals volume by density, right? So, or we can say volume equals, I'll take this here on the other side of the equal to sign. So this becomes mass by density, right? That is the relationship, you all know that. Now if I know the mass of the water, seawater, so seawater mass was 1225 tons, right? And the density of seawater is 1.025. So how much volume of water was I holding? 1195.12 metric cube. All right, so this is mass and that is volume. Right, so I was holding 1195.12 metric cube of seawater. This is seawater again. All right, now volume doesn't change, so volume remains the same. So that means this is the, also in this case, because the tank was full, right? Because the tank was full, this volume of seawater is equal to volume of tank in this case, right? Because the tank was full of seawater which weighed 1225 tons. So when I found out the volume of the seawater in this case becomes equal to the volume of the tank, correct? So volume of the tank is also equal to volume of seawater, which is equal to 1195.12 metric cube. Now why did I find the volume of the tank? Because if I replace it with dock water, So mass of dock water loaded, if I replace it with dock water, density of which is 1.005 tons per metric cube, how much mass of water did I load? So volume by density, right? Now volume is 1195.12. That is the total volume of the tank. So if I want to fill up the tank again, but this time with dock water with a different density, what do I do? 1.005, right? And what do I get? 1201.1 tons. So when I fill the same tank, so in this case, let's understand this very carefully. This is the same tank. All right. Same tank. The volume is 1195.12. Volume is 1195.12 in both the cases, right? When I put in seawater, when I pump in seawater, mass of seawater equaled 1225 tons. When I pump in dock water, the mass has now become 1201.1 tons. Right? Although in both the cases, the tank is full of water. The tank is full of water. But what has happened is mass has changed. How much has the mass changed by? 1225 minus 1201.1. How much is it? What's the difference? Almost you can say is 23.9 or 24 tons. This is in one tank. Now imagine that there is a ship here, right? And it has tanks on either side, port, starboard, maybe a forepeak tank, an aft-peak tank, and it has tanks everywhere, right? Only in one tank, when I change the density of the water, the difference was 24 tons. 24 tons is considerable when it comes to any kind of list or trim calculations. And this is, I'm taking a tank of a reasonable size. Imagine bigger tanks of bigger capacity. So if we do not consider the density, there could be unequal weight distribution, which will cause list or trim of the vessel, which you will not understand why it is happening. And that is why sometimes vessels often develop angle of roll, because when you consider multiple tanks and the impact of density and the weight distribution on multiple tanks, and if you don't take that into account when you are doing your stability calculations, then there can be an unexplained weight on the vessel. Alright, as a chief officer, you have to make sure you are aware of the weight distribution on the vessel so that it doesn't cause unexpected trim or list of the vessel. That is why, as a chief officer, it is your duty to check the density of the dock water that your ship is berthed in. You can check it multiple times. You should check it from an area where the water is not polluted. Ask the cadet if you want to. You yourself should be checking it, but making sure that you do take into account the density of the water before you start your stability calculations. Thank you for watching today's video and let me know what you thought about it. I look forward to your comments and feedback. Bye for now.